It's good that part wasn't recorded. It's my pleasure to introduce Hélyette Geman, who's going to talk about history. I do love history. And she's going to talk about the history of the CGMY model. Carr, Geman, Madan, and your. Thank you.
Okay, thank you, Jim, for the introduction. I first want to say that I am honored and moved to be here in honor of Peter. The testimonies of the students yesterday and the persons from Tandon were very moving, and the words of Peter's brother, Jim Carr, were exactly right. Peter was passion, generosity, kindness in any order, depending on the time. And I have to recognize, sadly, that in the name of the model which is there, the two extreme letters are gone. And I would like to salute as well the memory of my friend and co-author, Mark Yo, who was so useful to many of us, and not only in France, but on this side of the ocean, but where he came upon the invitation of Peter to visit Morgan Stanley in a kind of free, generous manner. And we lost two of them, unfortunately, and we will try to keep their memory alive. So I want to say also that I apologize if my own results appear sometime on the slides. I wanted to reconstruct the history. And as French people, like Jim, we like very much the history of science, and modestly, there is some science there. And I truly believe that 20 years ago, 25 years ago, we had so many potential results to find with the tools of probability in particular, and we were lucky to be there. And I would not necessarily say that about the current period. I know a little bit of machine learning that I follow with my students, but I believe that this was a kind of deeper. So how come this does not work? It seems not to work. Let me try this one. So, yeah, okay. So, time, stochastic time, appears like absolutely the normal thing in the financial markets. How can it be that the next calendar hour is going to be the same as the previous one? How can it be that the hours between 10 and 12 p.m. in London and the corresponding hours in New York be the same and the corresponding hours in Zurich compared to hours in the day when so many economies are vibrant and when we get so much information. So the clock cannot be calendar. So if we look at the mathematical aspect of time changes, we can recognize seemingly at first, I did some research on that, the name of Dublin. We are in 1940. He's of German origin, but he's battling with the French people. And at night, he's sending results, as you can see here, results in probability. So that's how it started. It continued with many names. Oh, by the way, in terms of specific results, you see the equation that Dublin exhibited in particular, and the work is at the French Academy of Sciences, and where essentially he he writes what he calls the fundamental martingales as time change Brownian motion. So time change was already there. You recognize W at a time, which is a random transform of the calendar time. Then Volkonsky used time changes to analyze Markov processes. Obviously, Ito McKean, in their beautiful book in particular, showed that time changes allowed to replace the study of diffusions by the study of Brownian motion. So basically, we have again and again in our field of mathematical finance, Brownian motion time changes. And in the first Bachelier World Congress, I had the honor to organize in Paris in 2000. Henry McKean gave a beautiful talk about time and scale. And that's exactly what it is about, and as well represented by my chairman and by many other people in the room or online. Then we get closer and we get this remarkable result that by Dubins, Schwartz on one hand, Dambis on the other, that any martingale is a time change Brownian motion. And as we know, martingale are important to us. And as I say, Brownian motion has no secret for some people, in particular, my friend Marchior. Then we have another result by Lamperti about the exponential of a Levy process. And we heard about this during these 2 beautiful days. And he showed that the exponential of a Levy process can be written at the time change Markov process. And lastly, a result by Monroe, 1978. Any semi-martingale is a time change Brownian motion. And this is the crucial one for us, because under no arbitrage, the discounted prices are martingales under an equivalent measure. Hence, they have to be a semi-martingale under the real measure. And Marchior was not aware of the result. It was in 1997, I was visiting the University of Massachusetts, and there was a probabilist there by the name of Joe Horowitz, who told me I was mentioning my research to him, and he brought my attention to this result. And finally, as you know, in a completely independent manner, in harmonic analysis, somebody by the name of Buckner, who is well known, introduced subordinators. But as we know, subordinators are constrained time changes, and we like the full generality of an increasing process almost surely, as opposed to the mathematical constraints posed by subordinators as they were introduced and continue to be used. So that's what we had. And then going to the results, in my own case, having the honor to work with Marchior, we, in the early 90s, it was like everybody wanted to find the price of the Asian option, where the stock price is a geometric Brownian motion, and the arithmetic average is not, and the arithmetic average is the one which is traded. And in fact, this is after this work that I went into the world of crude oil and so forth, because we have essentially averages, arithmetic averages in the world of commodities where we consume over time, as it is obvious. So in any case, so the sum of geometric Brownian motions is not a geometric Brownian motion, but Marchior has worked with Jim Pittman on the other side of the US continent, and on processors called Bessel processors and squared Bessel processors. And one day he brought to my attention the fact that the Brownian motion could be written as a time change squared Bessel. And the squared Bessel processors have the property of robustness under additivity, And this, with other elements and measure changes, allowed us finally to exhibit in a closed form the Laplace transform of the option price, Laplace transform with respect to maturity. And because the Greeks are linear and Laplace transform is linear, we were able to obtain the Greeks with the same precision, as opposed to Monte Carlo, where it gets less and less precise when you go further in the number of partial derivatives. And at the time, I was not working yet with Dilip or Peter, but with Alex Eidolon, whose name was mentioned before, we were able to invert the Laplace transform, in fact, by going to the Fourier transform, and we had the same dampening factor, and we were able to obtain the price. In the same paper with Marchior, which was way too long, we knew 1993 that volatility was not constant, and one problem we were interested in was the following. I am an option trader, my name is Nassim, and at day 0 I have sold an option on the basis of the Black-Scholes formula, and I put a price for the volatility equal to B, little b. And obviously in the real world, my volatility is going to be stochastic, and consequently, the time of perfect replication is a time, random time tau b, under which this equality is satisfied. And same thing, we were able to obtain the Laplace transform of the density of tau b under some models which existed at the time, in particular Hull and White and so forth. And as was mentioned in this conference, we know that, all of us know that in 2003 or so, we've got instruments called variance swaps, which allow you precisely to hedge on the wrong choice of the little b at date little t. And I want to mention the 2 papers by Peter on the subject of variance swaps, one with Lee in 2009, and one with Lee and Vu in 2010, 2 of his favorite co-authors and PhD students. So the minute I discovered this time change in a kind of theoretical way, I looked at the literature in those days of establishing the relationship between news, price changes, volume, volatility. And I'm sure that there are plenty of other results, which again and again express that transactions create volatility, transactions create volume, and so forth. So on this avenue, I looked also at what have been proposed for stock price processors. So we've got Fama, who observed that the closer the time interval, the more we deviate from normality as far as the stock return is concerned. Mandelbrot, after him, proposed stable processors as a better representation of prices and returns in finance. And remarkably, in 1973, and I advise you to read this paper if you have not, somebody whom I never met, and I would be happy to meet, but kind of answered Mandelbrot's proposal and say, no, that's not the way to do it. We want to keep finite moments, because in finance, if we don't have finite moments, we don't have variance, we don't have risk, and we need to start everything over. He was looking at futures contracts written on cotton, and in those days, he proposed a subordinated process for the log price. And he said, why So it was his intuition, but because you don't see in the paper any trace of the results I was mentioning at the start. So Y he assumed to be a Brownian motion, and he said X is going to be a subordinator to constraining, as I said, but representing the volume traded. So these were the messages of Clark. So with a former PhD student, we looked at this idea of recovering normality of return by changing the clock. And we have two papers, one on risk and one in Journal of Finance, where we tried to return to clock. And in those days, finally, for the second one, we had recovered the paper by Monroe. And now, by no arbitrage, we know that asset prices or discounted asset prices are martingales under an equivalent measure and semi-martingales under the P measure. And we use Monroe, and now we write the log price as a time-changed Brownian motion, and we say it has to be the case as long as the no arbitrage assumption we have been making over and over is valid. And with an A, we looked at two choices at the time, either driving the clock with the cumulative volume or driving the clock with the number of trades. And in the paper, we showed that the number of trades gave a better normality if we took the empirical returns and we extracted the W from the capital T we had chosen. Okay, you can do that. And to return to a previous talk this afternoon, the beauty of this transaction time representation is that using a simple result of probability, we can write the stock return as a mixture of normal, possibly infinite, and the mixing factor represents exactly the density of the time change, meaning accounts for the activity. I recognize, and I'm sure somebody is going to ask me, that in my slide, I made the assumption of independence. It's like we have two processors, the capital X may be driving the market as a whole, and okay, you manage just to separate the information between X and capital T. And we obtain this mixture of normal distributions. And I mentioned here a paper dated from 1994, where the author wants to test the mixture of distribution hypothesis by measuring the daily flow of information, which is exactly the message. And as was mentioned in a very nice talk, which was earlier, like the others, in the early 2000, 2001, 2002, Brigo and Mercurio, who are certainly known to many of you in this room, used two normal distribution, a mixture of two, to calibrate the volatility smile. And this afternoon, we learned that it was possibly better to have three in order to calibrate the W. And the good taste of Paul Glasserman and the speaker. Okay, then I met Dilip at a conference and we started working together. He started visiting France and whatever. And we had some papers where suddenly we wanted jumps. And we said the real markets move by jumps and pure jump processes are of finite variation. And we know that we can write the log price as a time-changed Brownian motion. And we say, W is continuous, obviously, we know that. If capital T is continuous, then obviously there is no discontinuity. But we say if capital T was continuous, it would satisfy an Ito types equation. And at the same time, capital T has to be increasing almost surely. So consequently, the second term has to go. If the second term goes, the time change becomes locally deterministic, and we don't want that. So consequently, we do not want a clock which moves by using only a diffusion. So these were the first requirements. Next, obviously, jump processors do not suffice. We wanted to do option pricing, and hence we want to levy processors, where we have the beautiful Levy-Khinchin theorem and the characteristic function, which is going to allow us to go to the Fourier transform of the option prices in a second stage. And K, the density, we wanted to recover all possible sizes of jump, namely the so-called infinite activity condition on little k. Okay, and then from that, we went to the CGMY process. Peter had joined. In fact, I had 2 slides mentioning another piece of work with Peter in the Journal of Financial Economics with Dilip and Peter, where we addressed the problem of incompleteness by introducing the argument of acceptability. So to return to the nice talk of Bob Jarrow this morning, the piece that he could not replicate, we would have asked this piece to be acceptable in the sense of a number of measures. Okay, we want that, and we showed that the bigger the position, the less acceptable it became, which would have avoided the whale of London for the CDO squares and so forth. Okay, so in any case, it was discussed kind of this morning by Bob. So let me focus on CGMY. And now we know that we want the density. We want 4 parameters, not because we are 4 authors, but because we want the first 4 moments. Okay, and as you see, we recognize that stock prices do not go down in the same way they go up. So consequently, we have 2 different expressions for the levy density, little x positive for the size of the jump, or little x negative. And then we have in the parameter capital Y some deep interpretation of the nature of the levy density, the infinite activity, finite variation, and so forth, that you may want to look at, if you will. So we did that first under the P measure, and we then moved to the Q measure, and we obviously had 4 different parameters in principle under the Q measure. We introduced directly the Fourier transform of the call price in terms of the log strike, and we had the same dampening factor, e to the power alpha k, and we were able to invert the Fourier transform, obtain the call prices, and then go to the volatility smile. And then we realized that the volatility smile was not captured as well as the time to maturity of the option, precisely because of the kind of rigid features of the levy processes in terms of their increments. And consequently, we decided to introduce stochastic vol in the levy process, but obviously we could not have like the Heston model or whatever, because we did not have any stochastic differential equation in our model. So necessarily the stochastic vol had to be created in another manner, namely with a stochastic time change. And that's exactly what we did. So I am mentioning here some features that we observed in terms of trying to go away from homogeneous Levy processes. And obviously, we wanted a time change for the volatility, which was increasing and which had the mean reverting property, which had been observed by Bates and Heston and so forth. Okay, so we took, obviously, the so-called CIR process, which, by the way, can be expressed easily in terms of a squared Bessel, but I have no time. And we took the integral of this positive quantity. And because of Pitt-Magnier, same paper, 1982, we had the form of the characteristic function. So we were in good shape. Again, we assumed independence, and we had our new process, capital Z, with some mathematics that I am going to skip for the sake of leaving a little time for questions. And we took consequently this Z process, time change Levy, and we tried for X, not Brownian motion, but we took CGMY, the Nick process, and the variance gamma, on which Peter and Dilip had been working on. And in those days, we had the data of Morgan Stanley, where I believe both Dilip and Peter were working. And we found that CGMY SV with stochastic vol was doing the best job. Okay, so I think I reached the time I wanted to spend on that and kind of making a summary of Brownian motion and time changes in our life. Bachelier, 1900, said the stock price is an arithmetic Brownian motion. Essentially, Brownian motion did not exactly exist in 1900, but the properties were clearly defined. Then we got Samuelson, 1965, transforming the beautiful results of Bachelier and choosing for the arithmetic Brownian motion the log stock price. Then we have the results on no arbitrage, saying that the discounted stock price is a martingale with many names, starting with Harrison, Krebs, Pliska, at the very small cost of changing the measure as long as they got the ID. And then finally, in the recent past, by no arbitrage, we have shown, a more recent past, we have shown that the log stock price is a Brownian motion as long as we are prepared to change the clock. So just to finish on something a little bit more new, and I will turn the floor to questions, if any. I am working with a PhD student in London on cryptocurrencies. I've been looking at cryptocurrencies for a number of years. And so these are, the clock is not changed yet. So here we are looking in 208 of the daily returns of Bitcoin. And if you see, what you can't see is that the density is slightly skewed to the left, because in 2017, at the end of the year, we had a gigantic rise when futures on Bitcoins were introduced, and then prices went down. And this explains why the density is skewed to the left, and certainly not normal, even for daily return. Now, if we look at the same time period, but intervals of 2 hours, we see that the deviation from normality gets more extreme. And this is Ethereum in 2022. And if you look carefully, it is big time at this moment, skewed to the left, including because of me. I had invested money in Ethereum because in principle, Ethereum involves what we call proof of stakes and should be better in terms of energy consumption and respect for the environment. So that was my choice. And finally, just explaining how we are trying to find the clock. We represent here the cumulative volume on one of the major exchanges of Bitcoin. They are traded 24 hours, as some of you may know. And we have some kind of linearity in the volume increase, which we do not like very much in terms of changing the clock. So that's where we are. And I would like to stop my talk here. Thank you.
Okay, so any questions here? Or online?
Okay, do we have any questions for Hélyette?
I'll lean back.
Oh, okay, yes. Oh, okay, sure.
Sorry.
Thank you. That was a very nice talk. This is not a criticism, but I noticed in the history you skipped a result which disagrees with the Levy assumptions, which is the Stanley Gopi Krishna 1999 work. And assuming returns are actually student 3 and not Levy at all, is there any comment you want to make about accommodating non-Levy price returns?
Okay, thank you. First, I absolutely need to apologize for at least not quoting 1,000 papers, and some of them written by people I know and really like. So that's my first answer. The second answer, if I understood clearly, your question was to say that we could do without Levy processes. Is it correct?
No, I was simply pointing out that the experimental work of Gopi Krishnan and Stanley argued that the price returns were well outside of the stable levy regime. So presumably the approach to dealing with the market returns is slightly different, or I don't particularly understand what you would need to do in terms of time.
Okay, certainly. As we know, we are proposing models, right? In finance, certainly, we are not proving that a result like in mathematics. That's why we should keep our modesty. And this is quite possible. I don't know.
Sorry, may I? Hi, how you doing?
Yes, hello.
So no, just tomorrow I'll answer Mike Lipkin on two things. Number one is that it doesn't make a difference in practice whether the process has a T is T or something. Fat tails are fat tails, and if you define fat tails as dominated by extremes, and how do you lose that property under summation, it doesn't make a difference what you use in practice. Because the difference between them would be if you have an aggregation of million data points between the two. This is what I say, distinctions without a difference, like Gopili Krishnan and Stanley, that paper is pretty much like sort of arguing about the how many bishops can dance on the head of a pin. Was Donald Trump or was that Donald Trump? That's sort of like that point. Tomorrow, I'll add that to my talk tomorrow. But second point, I want to make a comment on Clark, that Clark claimed that you need at least 4 moments or at least 2 moments to do price things. And in fact, Peter, my correspondence with Peter from 2005, I'll show a letter he sent me acknowledging that effectively all you need is the first moment to price an option, because all you need is a finite expectation, and all the rest is, nitpicking. And actually, you wrote a paper with a certain co-author with two co-authors, in which we say that all we care about is a tail risk, not the rest of the distribution. Okay, so risk, if you define risk as probability blowing up, then all the rest doesn't matter. All the moments, all these considerations are archaic and obsolete.
Okay, thank you, Nassim. So first, you remember everybody is here at 9 a.m. tomorrow and should not be late, because there will be nice talks, in particular Nassim. Secondly, to the defense of Clark, whom I never met, he is not trying to price options. He trades cotton futures and probably has risk management constraints. And we are in 1973, so I find pretty amazing that on his own, he came up with this relationship. But obviously, after that, many other results came along. And in the thing we have together, we were not either trying to price option. We just wanted to build a portfolio and look at the risk constraints. Thank you. Any other question? Julien.
Thank you very much, Hélyette. That's fascinating talk about like stochastic time change. Just a quick question. In the first slide, you mentioned at some point the result like any semi-martingale is a time change Brownian motion.
Yes.
But how do you generate a drift from just changing the time in the Brownian motion?
Brownian motion has no drift.
Yeah, but so semi-martingale has a drift. So I'm just curious. I mean, I don't know this result, so I'm.
It's embedded. It's not going to change much because the drift is a deterministic part. So if you go back to the embedded result of Monroe, I'm sure we can add the drift. Okay, so. Okay,
I will discuss later. Thank you.
Thank you. Yes.
Any more questions? So we have a few minutes before the next talk, don't we? Oh, yeah, sure. Oh, now. Better eyes.
Yeah, I should have mentioned the Sato process.
Okay, what about the Sato process? Yeah.
Right.
Why do we want to avoid locally deterministic functions?
Okay.
Would you like to repeat the question so that people read the question?
Okay, so I will read the question, sure. Why do we want to avoid locally deterministic functions? Hélyette, why do we want to avoid locally deterministic
Because we believe that the time change is going to reflect the market activity one way or the other, trading volume, individual trades, and consequently, we know that the market activity is not locally deterministic. There is no way we can know ahead of time.
So here is a friendly question from Dilip. What about the Sato process? It is also a CGMY contribution. Just hello.
Yeah, it's true. And Dilip mentioned the Sato processes yesterday. So I focused on my version of CGMY. What does he?
Dilip says.
Hello. He said hello.
Takes to reach T gives T.
I don't know.
Yeah, this is a mystery.
Yes.
I think he means Brownian motion evaluated. Okay, interesting. So I just wanted to say one thing, maybe add or maybe subtract from the little conversation you had with Nassim and Mike Lipkin. One can imagine that you devise an asset that can distinguish between jumpy Levy processes and continuous processes. And in fact, any barrier option ought to do, especially in the money barrier options. And if we really had the prices of those things, I think you would be able to distinguish. So it's not quite true that at any given horizon, it's certainly true that it doesn't really matter how you make the fat tail, but you can tell the dynamics, assuming people are pricing things right, from the prices of those barrier type things.
Thank you.
Another question?
With the martingale.
Oh, that's an explanation from Dilip.
Yeah.
Time with a martingale component is pure jump. Okay, thanks a lot for a great talk, Hélyette. And